So, let's go. Your brain evolved to count berries and dodge lions. That's it. That's what it was built for. Distances up to the river, timescales up to a season, quantities up to the size of your tribe. And today, we're going to feed it 10 real measured confirmed numbers from space that it was never, ever designed to handle. Weight you can't lift, speed you can't picture, emptiness you can't imagine, time you can't feel. Each one breaks a different part of how you think. Let's go. Number 1. A teaspoon that weighs more than every human on Earth. Take a star with more mass than our sun. Now crush it into a ball that fits inside Chicago, 20 kilometers across. That's a neutron star. And the stuff it's made of is so dense that a single teaspoon of it weighs about 5.5 billion metric tons. That's 900 times the mass of the Great Pyramid of Giza. 15 times the combined weight of every human being alive. And here's where your brain starts to glitch. Because this teaspoon doesn't look heavy, it's tiny, a teaspoon. But it weighs more than a mountain range, and your brain has no category for that. Massive things are supposed to be big. That's one of the first rules you ever learned. Neutron stars break it. The surface gravity is 200 billion times stronger than Earth's. The escape velocity is more than half the speed of light. The crust, and yes, it has a crust, is roughly 10 billion times stronger than steel. And the inside, we genuinely don't know. It could be pure neutron matter. It could be quark-gluon plasma. It could be something called strange matter that we've never observed anywhere. The instruments on the International Space Station are trying to figure that out right now, and they haven't cracked it yet. But the part that really cooks your brain, if you somehow scooped a teaspoon of this stuff and brought it back to Earth, you couldn't hold it. It wouldn't just be heavy, it would fall through your hand, through the floor, through the Earth's crust. And once it was free from the neutron star's gravity, the neutrons would start decaying into protons and electrons, and the whole teaspoon would explode. Oh, and the gold in your jewelry? Probably forged in a neutron star collision. You're already wearing one. Number 2, a single proton with the energy of a baseball. October 15th, 1991, a detector in the Utah desert picks up a single subatomic particle streaking across the sky. Probably a proton. One particle. And it's carrying 320 exa-electron volts of energy. 51 joules. That is the exact kinetic energy of a baseball thrown at 100 kilometers per hour. All of it packed into something smaller than an atom. They called it the oh my god particle. And I mean, what else would you call it? Here's how fast it was moving. 0.999999999999999999999999999999999999999999999999999999999999999999999 times the speed of light. 22 nines after the decimal point before you hit anything else. It was 1.5 femtometers per second slower than a photon. If it raced a beam of light for an entire year, it would lose by 46 nanometers. Roughly the width of a virus, 40 million times more energetic than anything the Large Hadron Collider has ever produced. And the LHC is the biggest machine humans have ever built. Now here's the part that still keeps physicists up at night. When they traced its trajectory back to where it came from, they found nothing. No galaxy, no quasar, no cosmic engine powerful enough to throw a proton that hard. One astrophysicist described it as having a gorilla in your backyard throwing bowling balls at you, except the gorilla is invisible. Worse, a particle that energetic shouldn't even be able to reach us. Physicists predicted back in the 60s that anything above a certain energy threshold would get shredded by the background radiation left over from the Big Bang. The oh my god particle had 5 times that energy. It shouldn't exist, but it does. And in 2023, a detector in Utah picked up another one. The Amaterasu particle, named after the Japanese sun goddess. 244 exa-electron volts, and this one appeared to come from the local void, a region of space with essentially nothing in it. Something out there is throwing baseballs made of single protons, and nobody knows what it is. Number 3. The magnetic field that dissolves you from 600 miles away. You know what a fridge magnet feels like? About 100 Gauss. An MRI machine is 10,000. The strongest magnet humans have ever built tops out around 450,000 Gauss. A magnetar, which is a specific type of neutron star, hits 1 quadrillion Gauss. That's a 1 followed by 15 zeros. 1,000 trillion times stronger than the magnetic field protecting you right now. And at that strength, the magnetic field doesn't crush you. It does something worse. It rearranges your chemistry. Within 1,000 kilometers of a magnetar, about 600 miles, the field is strong enough to stretch your atoms into thin pencil shapes. Spherical atoms become elongated rods. Molecular bonds don't hold at those geometries. Your body's chemistry simply stops working. Your nervous system shuts down because the electrical charges in your neurons are being pulled in opposite directions. You don't get crushed. You get chemically disassembled. You dissolve. At magnetar field strength, hydrogen atoms become 200 times narrower than normal. The empty vacuum of space around the star starts polarizing light like a crystal. The magnetic field itself has an energy density more than 10,000 times the density of lead. The field is heavier than lead. Let that sink in. And these things are dangerous at range. If you put a magnetar halfway between Earth and the Moon, it would wipe every credit card and hard drive on the planet. December 27, 2004. A magnetar called SGR 1806-20, sitting 42,000 light years away on the other side of the galaxy, had a starquake. In 1/10 of a second, it released more energy than the sun puts out in 250,000 years. From 42,000 light years away, the blast partially ionized Earth's upper atmosphere. It briefly turned our ionosphere from night to day. Fishermen in the Arctic saw a sudden aurora, and there are only about 24 confirmed magnetars in the entire galaxy. They burn out in roughly 10,000 years, rare, brief, and absolutely terrifying. But at least none of them are close. Number 4. 716 rotations per second. Take a star, a dead one. Heavier than the sun, denser than an atomic nucleus. Compress it to 20 kilometers across and then spin it. Not fast, not really fast. 716 times per second fast. 42,981 revolutions per minute. That's the pulsar PSRJ 1748-2446 AD, the fastest spinning star we've ever found. Its period is 1.4 milliseconds. For reference, a kitchen blender at full speed tops out at around 250 to 500 rotations per second. A car engine at redline hits maybe 6,000 RPM. This is a stellar corpse doing nearly 43,000 RPM. And it's not a disk or a blade. It's a sphere of nuclear matter wider than Manhattan. The equator of this thing is moving at about 16% the speed of light. 48,000 kilometers per second. If it spun any faster, it would fling itself apart. It's at 60% of the theoretical breakup speed, which means the universe only has about 40% of a headroom left before the physics stops working entirely. If you could watch it, you wouldn't see it flashing. 716 pulses per second is about 30 times faster than a movie projector. Your eyes would just see a steady glow. You'd never know it was blinking at all. And in 2025, a completely different team found a second neutron star matching that exact speed, 716 hertz, detected through X-ray bursts instead of radio waves. 2 different stars, 2 different methods, same absurd number. The universe apparently thinks this is a reasonable speed for a dead star. NASA is now developing navigation systems based on these pulsars because they keep time as well as atomic clocks. We're using dead stars as GPS satellites. Number 5, 93 billion light years wide, 13.8 billion years old. Here's where space breaks your sense of distance and your sense of math simultaneously. The universe is 13.787 billion years old. Light is the fastest thing that exists. So the observable universe should be about 27.6 billion light years across, right? 13.8 billion in each direction. It's not. It's 93 billion light years across, 3.4 times wider than it should be. The reason is that space itself has been stretching the entire time. Light left the edge of the observable universe 13.8 billion years ago, but while that light was traveling toward us, the space it already crossed was expanding behind it. The source that emitted that light was about 42 million light years away when the light left. That source is now 46.5 billion light years away. Space carried it outward while the light was en route. And this doesn't break Einstein. The speed limit applies to things moving through space, Space itself can stretch at whatever rate it wants. Think of it like walking on a treadmill that's speeding up. You're walking at the same pace, but the ground beneath you is covering more distance than your legs account for. Inside this 93 billion light-year sphere, there are roughly 2 trillion galaxies, 10 to the 24 stars. More stars than all the grains of sand on every beach on Earth. And all of that, every star, every galaxy, every planet, accounts for 4.8% of what's actually in there. The rest is dark matter and dark energy, stuff we've named but don't understand. And here's the real kicker, that's just the observable universe, the part we can see. If inflation models are correct, the whole thing could be so much larger that the observable universe is a rounding error. Number 6, 330 million light years of almost nothing. Everything so far has been about extreme presence, extreme density, extreme energy, extreme fields, extreme speed, extreme size. This one is about extreme absence. The boat is void, sometimes called the Great Nothing, a roughly spherical region of space about 330 million light years across. At average cosmic density, it should contain about 2,000 galaxies. It contains 60, 97% emptier than it should be. It was discovered by accident in 1981. A team was mapping galaxy positions to build a three-dimensional picture of the universe, and they kept finding a region where there was just nothing. A blank spot that wouldn't fill in. Here's the comparison that makes it real. Astronomer Greg Aldering said that if the Milky Way were sitting in the center of the Bacchus void, we wouldn't have discovered other galaxies until the 1960s. Edwin Hubble confirmed the existence of other galaxies in 1924. So the void would have delayed one of the most important discoveries in the history of science by 40 years. Imagine growing up on a planet inside that void. Your night sky is nearly black. The nearest galaxy is maybe 100 million light years away instead of 2.5 million. You'd have no Andromeda hanging in your sky. No evidence at all that anything exists beyond your own galaxy. The idea of other galaxies would be speculative philosophy, not science. It'd be like the multiverses for us today. And here's what's genuinely weird. The 60 or so galaxies that are inside the void are, on average, brighter than galaxies outside of it. Nobody knows why. Voids aren't rare, by the way. They make up about 80% of the observable universe by volume. The cosmic web of galaxies, those beautiful filaments you see in simulations, that's the minority. Space is mostly nothing, and the Bacchus void is the most nothing of the nothing. A cathedral of absence 330 million light years wide. Now, everything up to this point has been about objects with extreme properties, things that are too heavy, too fast, too magnetic, too big, too empty. From here on out, the measurements stop breaking your intuition about objects and start breaking your intuition about reality itself. Number 7, 1 hour equals 7 years, you're orbiting a black hole. A massive one, 100 million times the mass of the sun, spinning at nearly the maximum rate physics allows. You're on a planet just barely outside the innermost stable orbit, right at the edge of where matter can still circle without falling in. You spend 1 hour on the surface. When you leave, 7 years have passed for everyone else. This isn't science fiction. This is Kip Thorne's math, a Nobel laureate who calculated the exact scenario for the movie Interstellar. The time dilation factor is 1 to 61,362. For every hour you experience, 61,362 hours pass outside. That's 7 years. And it is physically possible. Time is not universal. It runs at different speeds depending on how deep you are inside a gravitational field. And this isn't theoretical, it's something we correct for every day. GPS satellites gain 38 microseconds per day compared to clocks on the ground. That's a tiny number, but without correcting for it, your GPS would drift by about 10 kilometers per day, useless within a week. In 1959, 2 physicists at Harvard measured time dilation across a 22.5-meter tower. The clock at the bottom ran slower than the clock at the top. Exactly as Einstein predicted. Your feet are aging slower than your head right now. The difference is billionths of a second over your lifetime, but modern atomic clocks can detect time dilation from a height difference of 1 centimeter. Astronaut Scott Kelly spent 340 days on the International Space Station. When he came home, he was about 5 milliseconds younger than his twin brother Mark. 5 milliseconds isn't much, but it's real. Time is not fixed. It's a measurement that bends depending on where you're standing. And near a black hole, it bends until it breaks. Number 8. Colder than the afterglow of the Big Bang. Space has a temperature. Most people don't think about that, but it does. The leftover heat from the Big Bang, the cosmic microwave background, fills the entire universe at 2.72, 5 Kelvin, negative 270.4 degrees Celsius. That's the baseline, the default temperature of everything. The Boomerang Nebula is colder than that. 5,000 light-years away in the constellation Centaurus, a dying star is ejecting gas at 500,000 kilometers per hour, 10 to 100 times faster than similar dying stars. That gas is expanding so rapidly that it cools below the background temperature of the universe, 1 Kelvin, 1 single degree above absolute zero, the point where all atomic motion stops. This nebula is the only known natural object in the universe colder than the afterglow of the Big Bang. It's so cold it actually absorbs heat from empty space. Space is warming it up. That's how cold it is. The reason for the extreme ejection speed is probably a companion star that spiraled into the red giant and dumped its gravitational energy into the explosion. The dying star isn't just dying, it's being murdered by its partner. And the violence of that process created the coldest place we've ever found. Some measurements suggest parts of it might be as low as half a Kelvin, half a degree above absolute zero. No biological process, no chemistry, no liquid of any kind can exist at that temperature. Even helium becomes a superfluid. And it won't last. The nebula is slowly warming as it ages. The record will eventually fall. But right now, today, there is a place in the universe colder than the universe itself. And it was named Boomerang by Australian astronomers in 1980 because it looked asymmetric through their telescope. Hubble later revealed it's actually shaped like a bow tie. They just happened to be in Australia and saw it from the wrong angle. Number 9. A single object heavier than every star in our galaxy. The Milky Way contains somewhere around 64 billion solar masses worth of stars. That's every star. Every sun-like star, every red dwarf, every giant and supergiant, all of them combined. Team 618 is a single black hole with an estimated mass of 66 billion solar masses. One object, heavier than all the stars in our entire galaxy put together. It's 15,300 times more massive than Sagittarius A star, the black hole at the center of the Milky Way. 10 times more massive than M87 star, the first black hole ever directly imaged. It was so far beyond the existing category of supermassive that astronomers had to create a new one, ultramassive. Its event horizon, the boundary past which nothing escapes, has a radius of about 1,300 astronomical units. Neptune orbits at 30. TON 618 could swallow our entire solar system about 40 times over without anything touching the edge. Voyager 1, after 47 years of travel, is about 165 astronomical units from the Sun. To cross just the event horizon of this black hole, Voyager would need to repeat its entire journey roughly 750 more times. And the thing is bright. It's a quasar, meaning it's actively feeding, and the accretion disk around it shines with the luminosity of 140 trillion suns. It outshines its own host galaxy. We literally cannot see the galaxy it lives in because the black hole is too bright. It was first cataloged in 1957 by astronomers in Mexico who thought it was a faint blue star. It wasn't confirmed as a quasar until 1970. Its light has been traveling for 10.8 billion years, and surrounding it, discovered in 2021, is a cloud of gas 330,000 light-years across. Twice the size of the Milky Way, just the gas cloud. There might be bigger ones out there. There's a candidate called Phoenix A that could hit 100 billion solar masses, but that estimate still needs confirmation. What's confirmed is Tehuis 618. 66 billion suns. One object, heavier than everything you've ever seen in the night sky combined. Number 10. All of human history in the last 14 seconds. Carl Sagan came up with something called the cosmic calendar. You take the entire 13.8 billion year history of the universe and compress it into a single year. January 1st, midnight, the Big Bang. December 31st, midnight, right now. On that calendar, the Milky Way forms around March. Our solar system doesn't show up until September. Earth forms September 6th. The first life appears around September 21st. And then everything you've ever heard of in a history class, every empire, every war, every invention, every person you've ever loved, all of it happens in the last 14 seconds of December 31st. The moon landing, the internet, this video, the last second. And here's a trick that shows how broken your brain is at these scales. 1 million seconds is 11.6 days. 1 billion seconds is 31.7 years. Your brain hears million and billion and files them both under big. They are 1,000 times apart. The future is worse. Red dwarf stars, the most common type in the universe, about 75% of all stars, burn so slowly that not a single one has ever died. The universe is not old enough. The oldest red dwarfs lit up shortly after the Big Bang, and they'll keep shining for 10 trillion years, 700 times longer than the universe has existed so far. Star formation will end in about 100 billion years. The last red dwarfs will flicker out in about 12 trillion years. That's all solid science, established astrophysics. What comes after gets more theoretical, but the current best models say this: after the last stars die, only stellar remnants remain. White dwarfs, neutron stars, black holes, all slowly cooling in absolute darkness. And eventually, over timescales so long we measure them in powers of 10, even the black holes evaporate. Hawking radiation bleeds them dry. The last black holes vanish in about 10 to the 100th power years. A Google. A 1 followed by 100 zeros. After that, the universe reaches maximum entropy. A thin, cold soup of photons and stray particles, each one separated from its nearest neighbor by distances larger than today's entire observable universe. Nothing happens, nothing can happen, and nothing will happen for longer than any number you could write in your lifetime. Every one of these 10 numbers is real, measured, confirmed, and not a single one of them was designed for a brain like yours. The fact that you followed all 10 might be the most impressive measurement on the list.